Hello, everyone. So, today we're going to get into the first steps for solving a truss. But, as you'll notice, the picture here doesn't look very much like a truss, because we're going to apply the same basic principles, but with a simply supported beam instead, because it's a little easier to understand. So, you'll see we have a pin, a force, and a roller. And you'll see that that force isn't centered in the middle of the beam. So we have to use our truss calculations to solve this simply supported beam. The first step is we have to start labeling things. So we have to replace our pins and rollers and turn it into a free body diagram with vectors. And we have to label this force at point B. So we're going to label that force FBY. Capital F because it's a force, and then subscript B because it's at point B in the Y direction. Remember that a pin, that little triangle symbol, has two reactionary forces, one in the X direction, one in the Y direction. So we're going to replace this with RAX and RAY. Now you may be asking, Mr. Bolin, why are we calling these R instead of F? Because remember, pins and rollers have reactionary forces. It's a specific type of force. So instead of just calling it a generic force, capital F, we're going to call it a reactionary force, R. And then it's at point A, so RA. And then again, Y direction, X direction, RAY, RAX. Okay, with me so far? A roller only has one reactionary force. So this roller, think about it like a ball. If you pushed on a ball that had something laying on it on the side, it's still going to roll. That's why it's called a roller. But if we push in the opposite direction of whatever's laying on it, it's just going to squish. So a roller's reactionary force always goes perpendicular to the beam or the member it is attached to. So that means our reactionary force either has to go down like this or up like this. So I'm going to start out with my reactionary forces always pushing against whatever's pushing on them. So that's why I have RCY here pushing up. Again, reactionary R at point C in the Y direction, RCY. Now these are the three equations that we're going to use to solve everything in trusses. Sigma means sum. So sum of the moments, capital M, always has to equal 0. Remember we previously talked about moments being that twisting force, that torque on an object? Sum of the forces in the X direction has to equal 0. And sum of the forces in the Y direction has to equal 0. That's because we're talking about statics, static equilibrium. So nothing here is moving. So remember, we always start these calculations with sum of the moments. And 9 times out of 10, I'll tell you if we ever get a weird one, but every time I typically give you a problem, we're going to look at the sum of the moments around the pin. And remember, point A was our pin, because that gives us the least amount of unknowns. We have to find the moment at B and the moment at C. Remember, our moment formula is moment equals force times distance perpendicular. And a positive moment is one that causes a counterclockwise rotation. A negative moment is one that causes a clockwise rotation. So since we know everything at point B here, let's solve for the moment of B first, just as practice. So moment of B equals our force, FBY, times 5 feet, because that's the distance from point A to point B, is 5 feet. we know that FBY is 100 pounds of force times that 5 feet. That's going to give us 500 foot-pounds of force. And this is negative because this causes a negative moment. It goes in a clockwise direction. Moment at C, we don't know everything yet. We know the total distance from A to C is 20 feet, but we don't know what RCY is, so that's what we're going to have to solve for. So we sub in what we found. Moment B is negative 500 foot-pounds, and the moment of C is 20 feet times RCY. Now we just have an algebra equation. So to solve for RCY, I'm going to move my negative 500 foot-pounds to the other side of the equation. So I'm left with 20 feet times RCY equals 500 foot-pounds. I'm going to divide by 20 feet. So then I'm left with RCY equals 25 pounds of force. Now that I have that piece of information, I need to update my free body diagram here and label what RCY equals. So I have RCY, I have FBY, I don't have RAY or RAX. So remember we had the sum of the moments has to equal 0, the sum of the forces in the y direction has to equal 0, and the sum of the forces in the x direction has to equal 0. So let's start with y. Sum of the forces in the y direction must equal 0. So that means RAY plus FBY plus RCY all have to equal 0. And then we'll sub in what we know. We don't know RAY, so we keep that one. We know FBY is 100 pounds of force in the negative y direction, and RCY is 25 pounds of force in the positive y direction. Then we just have some simple math. We have to move the 75 foot-pounds to the other side to solve for RAY. And we get that RAY equals 75 pounds of force. Then we have to update our free body diagram again. So we're almost finished. We just have to figure out what RAX is. So we know RAY, FBY, RCY. We did some of the moments, some of the forces in the y direction. Now we have to do some of the forces in the x direction. This is the easy one. Because what forces do we have in the x direction? Just RAX. So that means RAX has to equal 0. There's nothing else to cancel it out. So we update that. Now all of my vectors, let's double check. At point A, I've got RAX accounted for and RAY accounted for. At point B, I've got FBY accounted for. And at point C, I've got RCY accounted for. That means all of my vectors have a value. That means we've fully solved this simply supported beam. Congratulations! So this is the exact same process we're going to use when we use trusses or any other beam that doesn't have it centered right in the middle. Okay? So the next step is what happens if my force at point B comes in at an angle instead of being perfectly in the y direction or perfectly in the x direction. We'll talk about that in the next video.